So we have the double integral over S of, what did you say? Z ds, that's it. But what was Z? Z was 5, wasn't it? Z was 5. So double integral over S of 5 ds. And Z was 5 because we were up there, right? And take the 5 out, and this is 1 ds, and that's just the surface area of S. And that, be careful on that, that is pi r squared. What's the radius of that? 4, right? So the radius of this circle being 4 is pi r squared. 16 pi is its area. So we have 5 times 16 pi, which is 80 pi, by no coincidence. So I would say, yeah, there's a little bit of trouble there with the curl computation. You do have to be careful with that. But I do prefer that. I do like that compared, to what I would have done with the line integral. And it's amazing that it didn't matter what you would have used for your surface there. You could have used like a top hemisphere. As long as that was the boundary, it would have still worked. All right. What do y'all think? That's the line integral. Yep. Over the vector field. It's work. It's work. Okay. Yeah. If the field, it depends on what your field is and stuff, but you could look at it as work. Yeah.
When you find the magnitude of the flux vector, what is that going to be? Is that going to be just a scalar of the flux? Is that what it is?
Well, the flux is a number.
So when we find the magnitude, that's the actual flux. So that's what it's going to be.
I'm not sure.
Say that we have that vector, right? We came up with it, the one that you did the determinant for.
The curl?
Yeah, the curl.
The curl of F. What about it?
So that's going to be, the magnitude of the curl is going to be the flux, right? So that,
No.
I don't know if there's something I'm misunderstanding.
The magnitude of the curl, the curl of the vector field we're given is the new vector field that we're looking at in the surface integral. All right, let's go now and look at this. I have, I think, 2 examples or 3 examples in here. Okay, let's look at this one and appreciate the work we're not going to have to do. All right, so we have a line integral over C, where C is the triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and the vector field is given there. So we have, let me draw it first. Let's draw our curve in 3-dimensional space. 1, 0, 0 is here. 0, 1, 0 is here, and 0, 0, 1 is up here. So we're getting like one of the faces of a tetrahedron, right? But just that triangle right there. And we need to move around this C, right? And we want to know the line integral along that. And here's our vector field. Now, if you were not going to use Stokes' theorem, what would you have to do? You split it into 3 separate curves, right? You would call it like C1, C2, C3. You would have to find parameterizations for each of those curves, which are line segments, right? So we could do this. It's not impossible to do. It's just tedious, right? Then you'd have to evaluate your vector field on the curves, each for C1, C2, and C3. Then you'd have to dot those with the derivatives of the curves. And I mean, it could be done, right? It could be done. Let's see if Stokes' theorem is any easier. So if I'm going to use Stokes', I need to see if there's a surface that's the boundary of. Well, I think just that triangle, right? That surface right there, that triangle connecting the 3 points, that plane, right? It's a plane. That's what I'm going to call my surface S. And I can go a little further. It's flat, so maybe I could find its normal, right? And its normal should always be the same, because it's a flat sheet. It's always pointing in the same direction. I could do that. But at the end of it all, we're going to have to find the curl. So let's see if we can get the curl, right? I'm just thinking through this a little bit, okay? Like, okay, this is a surface. Am I going to have any trouble figuring out what that surface is? No, I've done this before, right? I've figured out how to find the equation of planes. It's not terrible. But the curl part might be a little messy, so let me go ahead and do that. Partial with respect to x, partial with respect to y, partial with respect to z. And x plus y squared, y plus z squared, z plus x squared. I'm going to let you do this on your own. I'm not going to do it up here. You should get negative 2z, negative 2x, negative 2y. So there's our curl. It's not so bad when you work through it. All right. Good. Now? I can find the normal vector, right? Let's see. If I find the normal vector, I'm going to have to do some vectors and cross them, right? I find some vectors. We've done this, right? Way back chapter 10 is where I first did this, right? So again, I'm going to save us some time. If you were to take some vectors in here and cross, you would get a normal vector of 1, 1, 1. Here's the reason I'm not going to proceed with that super shortcut. The reason I'm not going to proceed is because what kind of saved our ass last time was that a lot of these got zeroed out, right? And the one that was left always seemed to contain the variable that was fixed, right? Like when x was 2, it turned out to give us 4 times the area of that circle thing back from earlier. Or if x was 0, just zeroed the whole thing out. Do you see that if I do normal dotted with this, do you see that nothing's going to go away nicely? So what I'm going to do instead is I'm going to use this normal vector to come up with the equation of this plane. And again, we could do that because we know all the points, right? This is the normal vector. So it should look like, 1, x minus x naught, 1, y minus y naught, all that stuff. If you do all that, I'll just use this point right here, 0, 0, 1. You get that. And so you come up with x plus y plus z equals 1 when you put them all together. Now what value does that give me? If I know the curl, right, that's my new vector field. And my surface S is given by this equation, what can I do?
Solve for one of the variables.
Solve for one of the variables. Which one would you like to solve for?
Z.
Z, right? Make z a function of x and y. And now you're doing what we started class with. You're doing a special case of a flux problem right now. The only thing that's changed is this, where that came from, right? So I'm doing the following. The line integral over C of f dr has become the surface integral over S of curl of f dot ds, but that has become a special case where I'm going to integrate over d And I'm using a special formula from 13.7 when my surface S can be written as a function of two variables, which is 1 minus x minus y. That's this solved for z. So there's my special function of x and y. And what's my PQR? Here, right? Don't make that mistake. PQ and R comes from your curl. So this is my PQR. And I'm using, let's see, g of x, y, the top one. My normals are pointed up. Yes?
Why is that a y?
Y is where a y?
Where you dotted the normal in the quick equation?
Where I dotted the... Oh, why is this z? Yeah, sorry, this should be z. Thank you. I did it right here. I just didn't do it right there. All right, so we good? Y'all okay with the normals are pointed upward? The z components of any vector on that plane in that octant there are going to be pointed up a little bit. All right, so I'm using the standard formula, which is negative p partial g with respect to x minus q partial g with respect to y plus r dA. So negative p for us would be 2z, but then times the partial of g with respect to x, which would be negative 1. Then minus q would become plus 2x, but then that's it. Oh no, partial of g with respect to y, which would be negative 1. And then finally, plus r minus 2y dA. Let me clean that up. They're all negative? They're all negative? Do you want me to pull a negative one out or just leave it? Pull it out. Negative double integral over d of 2z. I'm going to leave a space here intentionally. Plus 2x plus 2y dA. This integral can only have what variables in it? X and y, because I switched, right? I'm a special case. That's what z is. So I want to replace this z with 1 minus x minus y. So please remove this 1 minus x minus y, and something real nice is about to happen. I believe the 2x, this is going to give us a negative 2x, and it's going to cancel, and a negative 2y, which is going to cancel, and all you're going to be left in here is a 2, right? So here's where we are now. We have negative, and how about the 2 that's in there? Can I pull that out? Negative 2, double integral over d of 1 dA. And that is the area of D, which is where? It's the base of the tetrahedron, because that D was going to be the restrictions on x and y, right? And that would have been from looking at the ground and looking at the projection of this triangular plane down onto the xy plane, and it would have looked like this. 1, 1, right? And it would have come across like that. And the area of that is 1/2 base times height, so that would have just been 1/2, right? Times negative 2. So the answer is negative 2 times 1/2, which is negative 1. Understand? Whew, 20 minutes. I was going to give you a chance to work one on your own, but I don't think there's enough time. Did I have the homework up there for that section? That's it, right? I didn't put homework. Okay, what you should do for homework for 13.8. How about 13.7? You know the homework for 13.7, right? Okay. For 13.8, you should do like number 3. Maybe 5, 7, hold on. I think 5, 7, and 9 I did. So number 3, 5, 7, 9 is what I have on here. You can also do 11 and 13. All right, there's one last thing I want to show you since I've got 20 minutes, and this will be nice. We will have one day for divergence theorem. It won't take us the whole class, and we can talk a little bit about the final, and we're going to make it to the end of the book. I don't want to start divergence theorem today, though. All right, so here's kind of a cool problem. I found this doing a little bit of research on Stokes' theorem. Let's say that you have a cylinder, okay? And let's say this cylinder has the equation x squared plus y squared equals... Now I'll ask you, do you want it to be a general cylinder, or you want me to actually like fix the radius at something? You want to do general? Okay, let's call it... Let's not use r because we might need r. Let's just call it c squared. Is that okay? Some constant square. You want to do a? Okay, I'll do a. Just for you. Yes, that's okay. I'll do that. There you go. A squared. All right, now I have a curve, all right? C, which runs along the boundary of this cylinder. Goes all the way around. Starts here at this point, goes around the back side, comes back, and let's call that C, and let's give it that orientation right there. Got it? I'm not telling you what C is. It's any curve that you can think of that does that. Find the line integral over C of f dot dr. Oh, but I've got to get something real quick. Hold on. Got to get you the vector field. And this has to be done correctly or else it's not going to work. So give me just a second. Y'all can take a break. You can chat with your neighbors for a minute. Okay, you ready? I'm going to give you the vector field. 2xz minus 2y. Two xz minus 2y. Two yz plus 2x. X squared plus y squared plus z squared. All right, I'm going to read this out. Someone just make sure I've got this. First component, 2xz minus 2y. Second component, 2yz plus 2x. Third component, x squared plus y squared plus z squared. Okay. All right, so I'm going to put that vector field over here so it's a little easier for me to work over there. 2xz minus 2y, 2yz plus 2x, and x squared plus y squared plus z squared. That's my vector field, all right? That's F. And of course, this we said was x squared plus y squared equals a squared. A is a constant. C is that curve, right? So find the line integral over this, over that curve with that vector field. All right, so what sort of issues or concerns do you have at this point?
Yeah, normal.
Do you know what C is? Nobody has given you C, right? Nobody has given you C at all? If you don't know what C is, you can't find a parametrization for it, can you? If you don't know what it is? The best you can do is maybe use Stokes' theorem. But if you use Stokes' theorem, you need to be able to give me the parametric, some way of figuring out what that surface is, right? So you can start working. I'm not saying that the surface in between there, see the curve is not flat, so you're not going to be able to put a flat sheet right across it. You see that? Understand? So there's a whole lot of things you don't know, right? So this seems like almost an impossible problem at this point, because you don't know the parameterization of C, and you don't know anything about the surface between them. All right, so before I continue with this, I just want to show you on the side here a different surface, but it's going to be very similar to that. Let's say we have a cylinder that looks like this. Oh, that's supposed to be straight. Okay, so this we cut the cylinder, right? And this edge is, wobbling around. Okay, so that's kind of like the C is over here. Yes? Got me? And there's a bottom edge too, which you can't see there. Y'all got it? If we are to use Stokes' theorem, then Stokes' theorem says that if C goes around the edge of a surface, right, then we can use the theorem. If I cut a cylinder in two pieces, I actually have two curves that would enclose this surface, not just one. It's the curve on top here, C, which I said is going that direction over there. And then this bottom one down here, which I will call C2. All right, is that okay? I didn't call this one C1, but I'll call that C2, just so there's no confusion. So do you see that C together with C2 enclose the surface? But there's a problem, because in order for Stokes' theorem to work, when you're walking along the curve, right, the surface is supposed to be to your left. Do you agree? Now, if I walk along this curve, is the surface to my left? What's the surface? What's the surface? Right? So let me do this. How about, imagine cutting this and opening it up. That might help. If I cut it and open it up like this. All right, let's say these 2 points come together, these 2 points come together, right? So which direction was C2 in? Is it this way, like this? Which direction is C1 in? Or C? Would it be this one? See, look, what I did is I cut it right here. I cut it, and I just laid it open like this. Right? Hold on. This one is, yeah, this direction. C and C2. All right? You with me still? Now, if I'm walking along C, let's say pointing out towards us is where our head is, up here. The surface over here is to my left, right? But if I'm walking over here, the surface is actually on the other side. So what I need to do is reverse the direction. So how does that affect things? Let me show you. I'm going to write it down. After I write it down, maybe you'll see it. Do you agree, according to Stokes' theorem, that the double integral over S of f dot ds should be equal to the two line integrals. One that would be the line integral, let's say C was okay, right? Orientation, right? Because the surface is to my left. Plus this one, but the orientation needs to be backwards, which means if I reverse the direction, I subtract, don't I? So how about instead I write minus this over C2 f dot dr. Are you all with me? These two curves, C and C2, enclose a surface. They enclose this surface in here, which is the cylinder. Therefore, the line integrals along those curves should be equal to the double integral over the surface itself. That's what Stokes' theorem says we can do. I had to change the orientation of this curve because I've got to have the surface on my left side. So negative C2 runs that way, which keeps everything oriented properly. Understand? Now, if you said, well, wait a minute, go to the other side of the page, then it's opposite, then I would agree with you, and then all that happens is this one's minus and this one's plus. Okay. Which one? Yeah, they are both closed, actually, because I cut them and opened them up, but that was just to visualize it. These are closed, right? These are closed? I haven't drawn the one over here yet, but the one I drew and erased, they were both closed curves, right? Okay. Y'all okay with this? How's my time? Got 8 minutes. Should be able to do this, I hope. Okay, this is what I'm going to work with right here. I will admit to you, I know nothing about C, right? So there's not a whole lot I'm able to do here. C2 was any curve that I picked that was below it, right? Or above it. It's just a different curve that also goes around the cylinder. What's a nice choice for C2? How about a perfect circle that runs right through the origin, right through the x, y plane, just like that? What if I choose that to be my C2? Right? That I should know about, because I can find the parametric equations for this, can't I? I can draw this curve. It's in the YZ plane, has a radius of A, right? I should be able to draw that. So I should be able to get some information about this, right? That I should be able to get. This, I don't know, but that's kind of what I wanted to know, right? So the only thing really is, can I figure out something about this? Well, all I can hope for, damn it, is that the curl of f, that should be curl, the curl of f is something nice. That's all I can hope for. So you ready to do curl of f? All right, help me out with curl of f. Sorry, you see I forgot the curl f there? You can't, Stokes' theorem's curl, not f. All right, so what's the curl of f? Maybe we can do it without actually, if I just put the stuff up here, maybe we can do it quickly. Okay, so what do we get? Partial with respect to y of this, 2y minus 2y, which is 0. Okay, what about if I cover this one up? Partial with respect to x, 2x, right? 2x minus 2x, but change the sign. Who cares? 0. All right, and then this last one, 2 minus 2 minus, yeah, so that's going to be what? 2 plus 2 is 4, right? Be careful. It almost looked like 2 minus 2, didn't it? But it was, what, 4 here? Agreed? All right. I'm with you there. I'm with you there. That's the curl. Now, this is the tricky part. I would have to come up with some parametric representation of this surface now, right? Right? because I'm trying to do this, ds. Only hope I have is if I can turn that into the n, right? The n. And that is not necessarily easy to do. But I'm going to look at, I want to just erase in here, convert that real quick over to this. Curl f dot n dot ds, or times ds. What can you tell me about that the normal vector of any, if you take any point on that cylinder, what can you tell me about the normal vector? I'll try and exaggerate it. Here's the cylinder, right, in the room. Normal vector is on the cylinder, right? Is going to be any one of these. Now they change as you go around the cylinder. Do you agree? But what do they all have in common? They're all running like this, parallel to the xy plane, aren't they? As I move this thing around, they're all parallel to the xy plane, right? What about the curl of f? Tell me about that vector. It's straight up. And what's the dot product of two vectors that are always like that? 0. Do y'all see that? Yes? That's why it was very important that I pick the right vector field for this to work, okay? This wouldn't work with just an arbitrary vector field. So because this normal vector, when I take the curl of f and I dot it, these two are orthogonal, right? Orthogonal. That means their dot product is 0. And that means the left side is 0. Understand? Okay? So if the left side is 0, then that means that these two on the right side, right, are all that's left. Not that they cancel, they're equal to each other, right? So just move this one to the other side, right? And what you have is that so it's saying the work, basically the work around this curve in this particular vector field is equivalent to the work around this curve. And so now what you would do, because I only have 1 minute, I can't do it, is you would set up this one, because this one we can do, right? R of t equals, we're a cosine t, a sine t, 0, right? That's R of t. That draws me that circle, C2. This is C2. And then I need the derivative, right? Because I'm going to do, this is negative a sine t, a cosine t, 0. And then when I plug this in, I have to plug this into the field, right? And then that, and then dot. It turns out to be nice. I'm out of time. But there's a lot of like